Welcome to Estimations of Physical Quantities. We're going to start off with orders of magnitude. These can help us to make predictions about the answer to a calculation before we put the exact data in. That way we can get an impression of what the answer is likely to be, and we can see more easily if we've made a mistake. So for example, if we're calculating the gravitational potential energy of an object, we would do this calculation here. We can put in the mass, gravity, and the height. So for example, a vehicle in a tall multi-storey car park is going to be several tons, which is several thousand kilograms. It doesn't matter exactly how many thousands, because we can just put 10 to the power of 3 to represent the magnitude of 1,000. We can multiply that by gravity, which is approximately 10. We know that it's 9.81, and we would use that number when we were really doing the calculation, but to give us an estimate, we can just put 10. And then the height, again, that's going to be roughly 10 meters if it's a very tall multi-storey car park. So very, very quickly we can see that our answer is going to be something of the magnitude of times 10 to the power of 5. Might be a low number times 10 to the power of 6, or a high number times 10 to the power of 4, but it's going to be roughly times 10 to the power of 5. And the same thing we can do with speed. If we know that the distance travelled is, for example, 10 to the power of 4, and the number of seconds is, say, a couple of hundred seconds maybe, then we can use our understanding of algebra to cancel and give a prediction. Okay? So that is how we would use orders of magnitudes to make predictions about what our answers are going to be for a calculation. Okay, we can also use that sort of understanding to make estimates. Estimates where perhaps there is a lot of data missing, and we're using values that are helpful, that we know that are roughly right in ideal situations. So, for example, there is an old past paper question that asks you, what is the approximate speed of somebody who is jumping in the air? Now, a regular person can jump to about a height of 1 meter. Somebody who's an athlete can jump much, much higher than that. So let's use that as an estimate. So let's say that we're going to go 1 meter high and we're starting from a stationary position. We can do a quick SUVAT to identify which variables we're going to be using. So we have said that the distance is going to be 1 meter, so we've got that value. We're being asked to calculate the initial velocity, and we know that the final velocity is going to be 0 at the height at the top of their jump. We know the acceleration due to gravity. We're not interested in the time. So this would give no, not s equals ut plus half at squared. That would give v squared is u squared plus 2as. Rearrange for what we're interested in, which is u. There we have it. And then we can start putting our numbers in. So it's going to be the square root of, now this term here is going to be 0, so let's ignore it. It's going to be 2 times gravity. Gravity is approximately 10. And if they're going about a meter, then all of this under here goes to about 20. Is about 20. And we know from our square numbers that 4 squared is 16. We know that 5 squared is 25. So it's going to be slightly closer to the 4. So we know that the starting speed is going to be 4, roughly. Maybe 4.5, maybe a bit less. Let's have a look at the speed of a racing bike. So the speed of a racing bike is going to be not as fast as a car, but approaching the speed of a car. And a car goes about 30 miles per hour, which is approximately 13 meters per second. This is in residential areas. A bike can go about that. So we're expecting those sorts of speeds. We could go on and talk about the kinetic energy of the bike. So for example, kinetic energy is half mv squared. and we can use some estimates to calculate the kinetic energy of a bike, the half, and then the mass. We would use, let's say, the average mass of a person, which is about 70 kilograms, and then we would use that velocity, that estimate, and have that there. Okay, so we can use that, and we can put it into a calculator to come out with an expected kinetic energy. Okay, so useful data. So we're going to talk about some values that are useful to know. For example, if you're asked the kinetic energy of a racing cyclist, the 70 kilograms, that won't have been provided in the question. It's something that I know because I've done lots of practice questions. I'm familiar with that sort of data. It's the sort of thing that you get by just living and being in the world and paying attention. So I'm going to go through some of the things, some of the masses, distances, temperatures, times, electric currents, and volumes that you may not have come across yet, but are very, very useful to know. Okay, so we're going to start off, and I'm going to talk to you about mass. Okay, so the average mass of a human, males and females, and across the world, is about 60 to 80 kilograms. So I would always use the number in the middle, which is 70. Mass of a cat is a very useful one to know, just for comparing things. If you get an answer out and it's about the mass of a cat, and you can imagine in your mind, oh, okay, yeah, well, you know, that object, it is kind of as heavy as I would imagine a cat to be, then great. Sounds to me like you got the right answer. Cat is about 4 kilograms. So if you've calculated something and it comes out as 4 kilograms, and you think, you know what, this thing that I've calculated, it's heavier than that, then you can look back at your answer and you can have another go at it and see if you've made a mistake. These things are useful to know so that you can figure out if your answer is sensible. Is it a reasonable answer? An everyday object like a pencil, that is approximately 5 grams. We wouldn't express it in grams, of course, we'd express it in kilograms. So that would be 5 times 10 to the minus 3 kilograms. A brick, that's a very useful one. Okay, we can all imagine holding a brick, and a brick is about half the mass of a cat. We've talked about cars already. There are a couple of 1,000 kilograms. Small cars are about 1,000, and larger vehicles tend to be 2,000 kilograms. Earth, our planet, is approximately 6 times 10 to the power of 24 kilograms. All right, let's have a look at another type of measurement. So we've got mass. Let's have a look at distances. I'm going to change colour. Okay, distances. So we talked about human mass. Let's talk about human height. So the average across the world for males and females is between 160 and 175 centimetres for an adult. We talked about a pencil before. Let's look at a pencil again. The length of a pencil is about 20 centimetres. So if something comes out with the answer of 20 centimetres and you think, you know what, is it about the length of a pencil? Awesome, yeah, great. A football pitch is one that's often given. So a football pitch, and I am talking soccer. That is about 100 metres. Okay, so it's about the distance that you would run in a 100-metre race. Speaking of a race, a marathon is 26.2 miles. That is a very famous number. But what is that in metres? It's about 42 kilometres, or 42,000 metres approximately. The length and height of the UK. The UK is about 1,000 kilometres long from north to south, and about 500 kilometres width east to west. The USA, in comparison, is much, much different. It's approximately 4,500 to 6,000 kilometres in dimensions. More locally, Liverpool to Manchester is about 55 kilometres. Manchester to London is 400 kilometres. Okay, let's go back to blue for temperature. We're going to talk about some famous temperatures and some common temperatures. So the coldest temperature recorded is 0 Kelvin, or minus 273.15 degrees Celsius. That is the coldest that you can get. You can't get any colder than that. It's absolute zero. The hottest temperature ever recorded on Earth is 57 degrees Celsius. That was recorded in Death Valley in California in the early 1900s. Body temperature, a very good one. Body temperature, that is 37 degrees Celsius, approximately. Room temperature is approximately 21 degrees. It varies. It can be about 19 to 21 degrees Celsius. Boiling point of water. So water to steam, the temperature at which it boils or condenses, if you're going the other way, is 100 degrees Celsius. Boiling oil. So in chemistry, sometimes you'll use a water bath, but if you need to heat something to a higher temperature than 100 degrees Celsius, you're going to need to use a different fluid. So you can use oil, and oil boils at about 200 degrees Celsius, depending upon the type of oil, the quality of the oil, that sort of thing. So in chemistry, sometimes you'll use an oil bath, or you might use a water bath if you're trying to heat something and keep it at a constant temperature. Speaking of boiling oil, the human skin will burn and become damaged by heat starting at 48 degrees Celsius and upwards. At 48 degrees Celsius, you're going to need to be in contact with the temperature, with the heat, for about 5 minutes. But as soon as you get to about 65 degrees Celsius, it only takes about 1 second for your skin to be burned. Speaking of which, a nice hot cup of tea is usually served between 60 to 85 degrees Celsius. So notice that comparison there. So a hot cup of tea can burn you. Let's move across and have a look at some more data. So we've talked about temperature. We can talk about time. We were talking about races before, so let's go back to that idea. The 100-meter world record for men and women is approximately 10 seconds. So 10 meters per second, essentially, is the world record time on average. The time of period of 5 minutes is 300 seconds. So I can put an equals there. 5 minutes is 300 seconds. An hour, you can calculate this for yourself, but it is 3,600 seconds. A day is 86,400 seconds. A year is approximately 3 times 10 to the 7 seconds. And let's go back to races again. I had the 100-meter race. Let's have a marathon. A marathon, the world record for men and women is approximately 2 hours, which is just incredible. Very, very short time to run that sort of distance. And speaking of a very short time, the lifespan of an average person is approximately 80 years. So those are the sorts of times that are useful to know about. Let's have a look at electric current. So you notice that I'm actually going through the SI units here, and that's deliberate. So electric current, or electricity. Electric current, not a lot of these. In the UK, the mains in your home, the alternating current in your home is 230 volts. Your cooker, an electric cooker, will use 40 amps, which is huge. Your electric kettle, to make your cup of tea, will be about 10 amps. So compare that. Now, a kettle is a very power-hungry appliance, so a cooker even more so. Very often, a cooker is going to have its own dedicated electric hookup. It's not usually the sort of thing that you would plug in. when it's installed, you tend to wire it in. It's not installed with a plug, it's actually installed directly to the wall, and it's usually done by an electrician. So, and it's got its own dedicated cable that's very, very thick to handle that high current. Whereas something like a phone charger will typically use about 2 amps. Slightly higher if it's one of those high-speed charging chargers. And last one, let's talk about the amount of substance, which is usually measured in moles. So amount of substance, amount of a substance, or volume. 1 mole takes up a space of about 22 litres at standard temperature and pressure. So 1 mole of gas, essentially it's a large box. It's the sort of box that a computer monitor screen would come in if it was being delivered through the post. So a decent sized box. A cup of tea is about 300 millilitres. So remember that 1 litre is going to be 1 kilogram of water, because 1 gram of water is the same volume as 1 milliliter. Okay, so 1 litre, 1 milliliter, 1 gram, 1 kilogram. If you are into your baking, then you might know that a teaspoon is approximately 6 millilitres, and a tablespoon is approximately 18 millilitres if you're into your baking. Okay, so those values are very, very important to know. You don't have to memorize them, but the more familiar you are with them, the more use you're going to get out of them, and the easier it is going to be to look at your answer and think, is that appropriate? Is that the sort of number that I would expect to see? Can I compare it to something that I'm more familiar with? Yes, I can. Actually, you know what? That number is way too big or way too small. And that could be very useful indeed.